Now our great pleasure to introduce our first invited speaker for CAV 2017 in Heidelberg. This is Chris Hawblitzel. Chris has received his PhD from Cornell. He has been a senior researcher at Microsoft Research for quite some time, where he has done a number of influential works. His interests span programming languages, verification, operating systems, security, and he's been involved in a number of large-scale projects that have demonstrated feasibility of formal methods for real-world systems, and he's going to tell us about one of them today. So thank you for coming to CAV.
Thank you, Victor. All right. As Victor just said, this is a large-scale project that I'm going to talk about today named Everest, with a lot of people involved from a lot of different labs around the world, including INRIA, Carnegie Mellon, various Microsoft research labs, and people with a lot of different areas of expertise, so programming languages and verification, cryptology, systems, security. So the goal of the Everest project is to use formal verification to improve the security of the systems. I'm not actually one of the security experts on this project, but nevertheless I'll try to give a little bit of background to start with on what exactly it is, what sort of security we're trying to verify here. So in that spirit, let's get started and let's meet Alice and Bob. So let's suppose that Alice wants to communicate with Bob, and she wants to do so securely. And by securely, I mean with confidentiality. She doesn't want her secrets to leak to anybody. With integrity, so she doesn't want her data to be tampered with. And with authentication, so she wants to talk to the real Bob and not some fake Bob or some attacker posing as Bob. So she brings up her web browser, and web browsers since the 1990s have supported something that was originally called SSL, Secure Sockets Layer, and at some point changed its name to TLS, Transport Security Layer. People still often informally call it SSL. And TLS is officially up to about version 1.2, but there's a new version called 1.3 coming out. It's in the final stages of standardization, so hopefully that should be rolling out officially in the next year or two. It's already supported experimentally by some browsers. So let's say that Alice and Bob decide to use the new version, TLS 1.3, and Alice brings up her web browser, points it at https://bob.gov, and the computers start to send messages to each other. So just for fun, let's see what's in some of these messages here. So if they're using TLS 1.3, the protocol starts out with something called a Diffie-Hellman key exchange, which allows Alice and Bob to establish a secure secret key that both of them know but nobody else knows, so that they can use that key to encrypt the data that they send back and forth. So the idea is pretty simple. Alice chooses at random some secret bits A, and they're integer and elliptic curve versions of this. Let's just assume for simplicity that A is just a big integer. So Alice is not going to reveal A to anybody, but she's going to reveal something computed from A. So she'll take this constant G, raise it to the power A, take that mod P, and publish that on the network. And raising something to the power of A is something that can be computed very easily. Going the other way, computing the logarithm and trying to extract A from this number G to the A mod P is considered difficult. So by publishing this, she doesn't reveal the secret A. Bob, likewise, picks his own random secret B. He doesn't reveal it to anybody, not even Alice, but he reveals G to the B mod P. And by the way, these constants G and P here are known to everybody. They're actually published as part of the TLS standard. G is a small number, P is some very large prime number. So given what Bob has seen from Alice, G to the A mod P, and his own private secret B, Bob then computes G to the A mod P raised to the power B, again taken mod P. And the two mods are redundant. So this is actually just G to the A to the B mod P, which is just G to the AB mod P. Alice can do the same thing, taking what Bob's published and raising that to her secret A. So this is just G to the B to the A mod P, which is G to the BA mod P, which is the same thing that Bob computed. So now they both have this same number, G to the AB mod P, and nobody else has this number, because in order to compute this, you need some of this public data here, but you need at least one of the secrets A or B. So anybody listening to this cannot compute this G to the AB mod P, because they don't know A and they don't know B. So now Alice and Bob can use this shared secret to encrypt their data. But Alice still doesn't know exactly who she's talking to. She knows she's established a shared secret with someone, but this doesn't say who actually made up this random secret B. It could be Bob. It could be somebody posing as Bob. So the next thing we want to do is to authenticate Bob here. And we do this by first forming a certificate. This is kind of an offline process here, where Bob gets some trusted certificate authority to attest to the fact that say his identity, bob.gov, is connected with a particular public key for which only Bob knows the private key. And Alice can check the certificate, check that it's been signed by a certification authority that she trusts, and see that, yes, bob.gov is associated with some particular public key owned by Bob. And then Bob has to prove that he actually is the owner of this public key. He does that by signing some data with his private key. So typically, he'll just take the bits that have been sent so far, sign those with his private key, and Alice can see that only Bob could have done this. Only Bob knew his private key. So this communication must be happening with Bob and not somebody else. And then finally, we want to make sure that this data hasn't been tampered with. So Bob sends what's called a message authentication code, or MAC. And a MAC is just kind of a hash value of all the data that's been sent so far. So if we weren't concerned about an active attacker, we could just take any old hash of the data here, and then if any of the bits got flipped by accident, we would notice it. An attacker could flip some bits and then also update the hash to match the flipped bits. So in addition to just being a hash, a message authentication code mixes in some secret key material derived from the secret G, A to the B that only Alice and Bob know. So that makes sure that even if an attacker is tampering with the data, the attacker could not form a valid MAC. And therefore, Alice would not be fooled by any data that's been tampered with. So now Alice is exchanging data securely and secret with who she knows to be Bob. And she goes ahead and sends her own MAC to Bob, and then she can immediately go ahead and start sending some application data, which is encrypted and MAC'd using key material derived from this shared secret G to the AB mod P. So that's the basic idea behind how TLS 1.3 works. There are a lot of more features here. So they can exchange data to negotiate exactly which cryptographic primitives they'll be using. They can share keys ahead of time, resume previous sessions. There are various ways of authenticating Alice if she needs to be authenticated. Various schedules for turning key material into specific keys, updating keys, padding, error handling, and all that. So this is all written down in a specification. So there's a specification for TLS version 1.2, for version 1.3, and both of these are on the order of, say, 100 pages. So not trivial, but not terribly big. And the implementations of these, so for example, historically the most popular implementation of TLS has been the OpenSSL software. And to implement the protocol that I've just described, the TLS protocol, it takes OpenSSL about 40,000 lines of C code. Now that sits on top of a lot of cryptographic primitives for encryption, hashing, message authentication codes, and so on. So that's actually more than the TLS protocol. That's about 160,000 lines of C code for that. And it turns out, in terms of performance, the bottleneck is really in the crypto. How fast you do crypto determines how fast this protocol goes. So a lot of effort has gone into optimizing that C code and producing handcrafted assembly language code for various architectures for the most important cryptographic primitives so that it runs really as fast as possible. So there's a lot of legacy software as part of OpenSSL, old cryptographic primitives that people don't really use that much anymore. So people have gone in and cleaned this up a little bit. So there's something called Boring SSL, which is a fork of OpenSSL where they've thrown out a lot of the old legacy things, and this is probably about 200,000 lines total. So 200,000 lines is, you know, this is nothing like Linux or Windows here. This isn't huge. But it's big enough that there have been significant bugs in these systems before. So both in OpenSSL and other implementations of TLS. So you might have heard of Heartbleed, for example. This made the newspapers. And it was really just a very simple coding error, a buffer overread that attackers could use to steal pieces of memory that might contain secrets from servers. In another version of TLS, there was this embarrassing go-to-fail coding error that had the effect of skipping over some important security checks and then continuing the protocol as if everything was fine. And both of these are obviously very silly coding errors, but there have been more subtle errors that have to do with the protocol itself, where attackers have been able to put together sequences of messages in unexpected ways and undermine the protocol. So there have been attacks with names like Beast, Logjam, Triple Handshake, Freak, that took years for security researchers to realize were latent in these protocols. And finally, there have been bugs in the implementation of the cryptographic primitives, ranging from, you know, again, simple buffer overflows and coding errors to implementation errors that cause the cryptographic primitive simply to produce the wrong bits. And I'll show an example of one of those later. So one of the worst things about these bugs from a security perspective is that these are kind of silent bugs. When you're using TLS in the normal case, it looks like everything's working, even when these bugs are present. But underneath, there are actually vulnerabilities that attackers can exploit, and you don't know about them necessarily. So this seems like a very good candidate for formal verification. So this is the goal of the Everest project. And by the way, Everest is sort of an acronym: T for transport, S for secure, E for end-to-end, ver for verified, and E for Everest. So the goal of this is to check that our implementations, a real running, efficient implementation, is correct in the sense of, first, meeting the standards, and second, beyond just meeting the standards, actually proving that we have some strong security properties like confidentiality and integrity and authentication. So as part of this, we're trying to improve the tools that we're using to do verification, and we're looking in particular at F-star running on top of Z3, and we're also looking at lean. And we're not just trying to build, you know, a research artifact here. We're trying to build something that can be released and plugged into real pieces of software that people actually want to use. So as we go along, we're integrating the software. We've already integrated what we've done with curl, and, well, let's just say one of these web browsers and one of these web servers so far, so that we can see that what we're developing is actually usable here. So I'll describe some of the components of Everest as we go along, but very roughly, we have to implement the TLS protocol itself. We have to implement some sort of verified crypto, and there's a portion of this that we generate C code from. There's a portion of this that is handwritten assembly language code. We're also looking into some other aspects like correct certificate handling, some basic properties of HTTPS. I won't talk about those. So In fact, I'll say a few words about MeTLS, which is the TLS part of this, and Hacklestar, which is what we generate C code from for our crypto. Santiago already gave a talk at VSTTE on Saturday, giving kind of a broad overview of Everest. So I'm going to focus mostly on how we've been verifying assembly language with a tool that we built called Vale, which is verified assembly language for Everest. And then at the end, we've recently been porting our Vale code, which currently uses Daphne as a backend verifier. We've been porting that to use F-star as a backend verifier. So I'll say a little bit, a few more speculative words about automation and expressiveness based on our experience with that. All right, so let's start with MeTLS. So MeTLS is a project that predates Everest. It goes back to 2013. And the original idea was not to produce something that people would want to run in the real world, but to produce a reference implementation that real implementations could compare to, and that was verified for strong security properties. So the original version of MeTLS, it was runnable code written in F-star, but it was slow. For example, it compiled to OCaml rather than C. They spent a lot of times, the members of the MeTLS project spent a lot of times verifying very strong security properties of it, mostly mechanized, but sometimes with handwritten proofs as well. And this covered SSL version 3.0 up through TLS 1.2, and it just connected to kind of off-the-shelf unverified crypto. So the new phase of this project as part of Everest is developing TLS 1.3 support. So there are examples that MeTLS already has of this running. Linking with the verified crypto libraries from Hacklestar and Vale. So we have some examples of this running already. Compiling to efficient C code. So this is still very much work in progress. Rewriting the code so that, say, it doesn't use higher order functions and that kind of thing. And then verifying the resulting rewritten code that's been rewritten to be more efficient. So that's very much in progress as well. So that's all I'm going to say about MeTLS. Like I said, you can find out more if you go back and look at Santiago's talk or some of the papers on MeTLS online. So the rest of this is going to be on what we've done to verify cryptographic primitives that TLS is built on top of. And this includes popular symmetric algorithms like AES and Cha-Cha that are very fast once you've established a shared key, hashes and message authentications code like SHA, MAC, Poly1305. And people are now combining the symmetric encryption with MACs. So there's something called AES GCM that does both the crypto and the message authentication code. Various public key and digital signature algorithms like RSA and various elliptic curve algorithms. For all of these, our goal is to verify, well, first, obviously, of course, basic safety. We don't want to buffer overflow in this. But then we want to make sure that our implementations of these protocols actually meet the specifications that people have very carefully written down. And we want to make sure that they avoid any sort of side channels. We don't want them to leak bits of the key through timing or cache usage or anything like that. So I'm going to give just one quick picture of what Hacklestar looks like. This is what we use to generate C code for cryptographic primitives. So here's an example from the Hacklestar library for the SHA hash function. And SHA just consists of shuffling a lot of bits around until data has been mixed up really good into a small hash. So a lot of left shifts, right shifts, XORs, and that kind of thing. So the specification says things like, you should logically negate X, and that with Z, and X and Y together, take the XOR of these. And then the Hacklestar implementation simply implements that, and then that gets compiled to the obvious C code here. So Hackle star is written in a subset of F star known as low star that can be mapped very directly to C. And then the interesting part, of course, is verifying that an implementation like this actually matches the specification for SHA. So that's an example of Hackle star. I'm going to talk mostly now about what we've done, not with C, but with assembly language. And I'd like to use one of the other hashing protocols, actually a message authentication protocol, as a running example for the rest of the talk. So this is a fairly new cryptographic primitive known as Poly1305. And its goal is to take some data, which can be of arbitrary length, and hash that down to a small tag that's mixed in with some secret key data. So I've just shown the inner loop for Poly1305. The inner loop is actually very simple. So we repeatedly take 16 bytes at a time of data, add that to the current hash, which is this big integer h up here, multiply in some key material r. So this is this 128-bit number derived from the key. And then, so multiplying the hash value by r makes a big number. We then compress that number back down by taking it mod p, where p is the specific number 2 to the 130th minus 5, hence the name Poly1305. And the fact that p, this particular number p here happens to be a prime, helps protect against collisions. So when we take this big number h times r and compress it back down, we're kind of wrapping the number around mod p in a way that spreads the data very evenly out over all possible results and ensures that different data don't all clump to the same hash code here. So we want this to run as fast as possible, so we have to think about how to efficiently implement these mechanisms. Of course, computers are very good at addition. There are instructions for that we can use to put together big integer addition. Multiplication is also pretty fast. This last operation at first glance looks like it might be a little slow here. So in general, doing a mod operation requires using division instructions. Doing a big integer mod operation is particularly painful. But it turns out that not all mod operations are hard. Some of them can be computed using a few tricks. So let me give a quick example of an easy-to-compute mod. If you want to take a number and compute it mod 99, let's say the number 301, you can just observe that you can do this repeatedly by subtracting 100 and adding 1. So getting 202, 103, 4. And you'll notice that in each of these steps, the sum of the left digits 3 and the right digits 1 here stays the same, or at least the same mod 99. So rather than going through this process one at a time, you can just skip to the end, take the left digits, the right digits, add them together, and you'll get something that is much smaller than the original value, but is still equal to the original value mod 99. So this is a fun party trick that you can use if you ever happen to be at a party consisting of math students, for example. So you can extend this to things other than just, say, the number 99. If you want to do mod 95, you just subtract 100 and add 5 each time, so you end up with 5 times 3 plus 1. If you want to be really ambitious and do, say, 395, you subtract 400 each time, add 5 each time, and you get this kind of messy expression over here, which is still relatively easy to compute. I didn't choose this number 395 at random here. This is 4 times 10 squared minus 5. And if we replace the decimal digit 10 with something that computers like, so a 64-bit computer might like 64-bit digits, that's how big that's what can fit into a register, then we notice that this is just our number p, 4 times 2 to the 64 squared minus 5. That's 2 to the 130th minus 5. And this formula here is actually exactly what we need to compute or to reduce a large number mod p to a small number mod p. And notice that we've turned what used to be these kind of high-level mathematical operations, mod p, into what can be computed very efficiently with bit vector operations. So mod 4 is just taking something ANDed with the two lowest order bits, 3. And maybe a little less obviously, multiplying something divided by 4 times 5, that's just kind of like adding something to 1/4 of itself, as long as you round down to the nearest multiple of 4, which you can do with and bitwise negation, and the divide by 4 you can do with right shift. So all of this stuff, it turns out, we can actually do very efficiently on standard hardware. So if you go to an implementation of Poly1305, so for example, suppose you bring up OpenSSL's implementation of this, you'll find an implementation of C, you'll find implementations in assembly language for various architectures. So what I've shown here is part of the OpenSSL implementation for 64-bit Intel architectures. And as you can see, there are operations that correspond exactly to what we've just kind of deduced here. So there are AND and right shift operations up here, another AND operation corresponding with this, and then a bunch of add instructions to add everything up. So kind of what you might expect for carefully hand-optimized code here. So what we've done as part of the Everest project is to start taking code that people have already hand-optimized, like this OpenSSL code, and porting it to our own language, Vale. So this is the code that we wrote that corresponds exactly to the OpenSSL code on the left here. These are the same instructions. And I have to apologize. There are two different conventions here for which registry you put on the left and which on the right. So OpenSSL uses the convention that you move the left source operand into the right destination operand. We use the convention that you move the right source operand into the left destination operand. So apologies for that. But otherwise, you can see these are exactly the same instructions here. Now, just porting existing code to a different syntax wouldn't be very interesting. We actually want to verify properties of this code. So let me make some space for this here. So I'm going to actually have this procedure here expand to cover the whole slide. And I'll show you how we verify this. Before I do that, actually, I almost forgot. What I'm showing you here is what you'll find in OpenSSL if you look at the most current code. If you looked at it back in early 2016, there was actually a missing instruction here. They didn't realize you had to propagate the carry bits all the way to the highest word. So for a lot of their tests, for all the tests that they had at the time, they got the right answer. And then over the next month or two, people found that some other tests, this was actually giving the wrong bits. And so after about a month or two, they fixed this. So this is what we want to prevent by verifying this code here. So let's see what this looks like. So I'm going to take this procedure, which we're calling Poly1305 reduce. I've compressed all these 8 assembly language instructions into one line to make some space here. And then I'll show you what we do so that the Vale tool and Daphne underneath this can verify this code. So first of all, I've written some standard Hoare logic preconditions and postconditions here. I've defined some abbreviations up top. So n is just going to mean 2 to the 64. P is our prime number, 2 to the 130th minus 5. I've defined some abbreviations for register names just to match what OpenSSL did here. Apparently, it's too much work to type in a 3-character register name when you could type in a 2-character abbreviation instead. And I guess if you use more than 3 characters for anything, the code would become impossible to understand. So what we want to prove here is that what's coming in 3 of these registers, H0, H1, and D3, if you interpret that as a 3-digit big integer here, Hin, is related to what will come out in new values of H2, H1, and H0, which we call H out here, in the following way. We want this output to be equal to the input mod of P, and we want the output to be small. So we want its upper digit to be, say, less than 5. So in order to prove this, the prover is going to need a little bit of help. So we call some lemmas to reveal some facts about bitwise arithmetic, all those shifts by 2 and ands with 3 and so on. And then finally, once we've done all these instructions, we call one last lemma here to actually prove that, say, h out is the same as h in mod p. So I gave you kind of a proof by example a few slides ago. We need to prove this for real here. All right. So that's what Vale code looks like as an example here. I'll tell you a little bit more about Vale as a tool. So we designed this language Vale to be as extensible as possible, because we know we're going to have to develop code for a lot of different architectures, x86, x64, ARM, and stuff. So we don't want to have to keep changing the tool every time we use a new architecture. So Vale doesn't actually know anything about any particular architecture, but instead it has the programmer declare the meaning of each architecture by writing some code of their own in a language like Daphne or FStar or Lean. So I've just given a silly example of a hypothetical architecture with some registers R0, R1, and so on, some instructions for moving, adding, negating. In order to prove anything about this code, the programmer has to write down the semantics of these instructions, how they change one state into another state. And then finally, to be able to actually run the code, they have to write down a code generator that prints an abstract syntax tree consisting of these instructions here in a form that, say, GNU assembler or MASM can understand. So those are kind of the key ingredients that you have to write for each new architecture that you want to use with Vale. And once you've got that, you can write some actual Vale code. And Vale code consists entirely of procedures, like the Poly1305 reduced procedure I showed in the previous slide. And in fact, instructions themselves are just procedures with requires and ensures that say what effect each instruction has. And so the move instruction here is connected with this move over here, and this add instruction is connected with this add over here, and so on. And then once you've got proofs of these preconditions and postconditions for each instruction, which are proven in terms of the semantics here, you can start to prove properties of programs. The way that we actually carry this out is we take code written in the Vale language, pass it through the Vale tool, and this generates two things. So it generates an abstract syntax tree representing the code that you wrote here, say move, add, using the data type for instructions that you declared over here. And it produces a lemma with the goal of proving that, say, the ensures clause of the procedure holds if the precondition, the requires clause, holds. So Vale can produce this code and lemma currently as Daphne or FStar pieces of code. And then it gives this code over to one of these tools for verification. So for example, if we give this to Daphne, we will give the entire machine model to Daphne, the code and the lemma that were produced by Vale, any sort of high-level property that you want to prove about the code, you can write in Daphne directly. And so all of this machine model and the tools themselves are part of the trusted computing base that we rely on. Vale itself is actually outside the trusted computing base. The worst thing that it can do would be to produce, say, some bad code that fails to verify the property you're interested in. But that's okay. In that case, you just fix the code or fix the Vale tool and go on. It's not going to cause you to incorrectly verify code that's insecure. So because we have the Vale tool actually produce an abstract syntax tree of this form, we can now write additional tools independent of Vale that do additional transformations or analysis on this code. So last summer, a couple of our interns wrote a static analysis tool that looked for side channels. and particularly took this code, ran a standard data flow analysis on it, and says either, okay, this has no timing or cache side channels, or no, it may leak. And as part of this analysis, they produce a proof that formally, if the side channel analysis says that this is okay, and you have hypothetically two evaluations of the code from S1 to S prime and S2 to S prime, and these initial states here share the same public values but maybe have different private values, then the observable trace that an attacker can see by watching for timing and memory accesses will look the same at the end of this execution when you reach state S1 prime and S2 prime. So if the side channel analysis says that the program is okay, that means you can't learn the secrets that this code is trying to protect by looking at timing and memory accesses. I'm going to give you a slightly larger example here, and here I have to confess I lied a little bit when I brought up the Poly1305 code from OpenSSL. I referred to that as assembly language. It was actually a Perl file, not an assembly language file. So most of the OpenSSL code is written in the form of Perl scripts that generate assembly language code. And here's an example. This is the SHA code for ARM that really takes advantage of the Perl scripting abilities, let's say. So this is part of the inner loop for computing a SHA hash code. It's actually a Perl subroutine that gets called 16 times so that these 16 iterations are inlined. It gets called with different values of I from 0 through 15, and different registers in each iteration, which gets used by these instructions. So A is actually not the same in iteration 0 as it is in iteration 1. Instead, the values kind of rotate through the registers from one iteration to another. This is just more hand-coded efficiency here to avoid moving data between registers between these iterations here. And to top it all off, for some reason, it's using the C preprocessor to customize different iterations, so it does something different in iteration 15 than in the other iterations, for example. This is kind of messy code to reason about formally. You might be tempted just to run this Perl script, generate the instructions, and try to verify that, rather than to deal with this as is. But unfortunately, that's going to generate a lot more work for your verifier. That's 16 times as much code as you have to verify. So instead, what we've done is to use some features of Vale. So Vale is not only an assembly language, it's a macro assembler that you can kind of write macro procedures that take what are called inline arguments. So you can say that each of these operands, A through H, is an inline argument, and you can instantiate this procedure with various different registers for those arguments. And you'll see that we've kind of lined up our implementation so that it exactly matches the OpenSSL implementation here. But we're not using Perl. We're not using the C preprocessor. We're using something more like partial evaluation, where we have if statements that can be evaluated at macro expansion time here. And the nice thing about this is that from a Hoare logic point of view, these just look like ordinary if statements. We can verify them first and then macro expand them. So this ends up being a fairly small procedure that we can verify fairly quickly, 20 or 30 seconds or something. And then there's another procedure that we have to verify here that actually unrolls 16 calls to this procedure here, and it just does that by calling itself recursively. So given an I, it calls itself recursively on I plus 1 up to I equals 16. And it rotates these registers that it receives, so there's different registers in each iteration. So this is what we're doing here, trying to make sure that we absolutely match exactly the code that OpenSSL uses here and get every bit of performance that we can out of this. So in fact, we do. So we've made some measurements of the performance of this, both for the Poly1305 code that I showed earlier, or I showed a very small snippet of earlier, and the SHA-256 hash function for ARM that I just showed on the previous slide. So those are basically the same code as OpenSSL. They have the same performance. There's a little bit of difference in the C and assembly language code that wraps the OpenSSL code that we ported. So that's why these bars aren't exactly the same. We also wrote a version of AES that uses the built-in hardware instructions provided by Intel for AES, and that also runs as fast as the OpenSSL version. I have to give one caveat here. So these two versions of Poly1305 and SHA here, so this is optimized hand-coded assembly language, faster than C code. It's not quite the fastest code that OpenSSL has available, because we don't yet use the vector SIMD instructions. But we're still working on that. So these were the non-SIMD versions that we ported from OpenSSL. All right, so that's all I have to say about our verified crypto. To kind of wrap things up, I want to talk about something that's a little more speculative here. And this is based on our experience recently. So everything that I've described so far, we've written Vale code that uses Daphne as a backend verifier to verify this code. And we've recently been switching to FStar, so we've been rewriting our machine model in FStar, having our Vale tool generate FStar code when it generates these code values and lemmas. And this is not because there's anything wrong with Daphne. It's just because MeTLS and Hacklestar are already written in FStar, and we're trying to converge on a single unified language here. But this has kind of given us an opportunity to reflect a little bit on well, an old paper here from 1992 referred to as two classes of automated reasoning systems. So I'll just give you a quote from this paper on PVS here, 25 years ago. Automated reasoning systems typically fall in one of two classes, those that provide powerful automation for an impoverished logic, and others that feature expressive logics but only limited automation. And then they point out that PVS attempts to tread a middle ground between these. So that was a long time ago. Nevertheless, I would claim that a lot of verification projects are still kind of distinctly split in these two classes. So I'm kind of a systems guy. I go to OSDI and SOSP. So I went back and looked at the last 10 years, and there were 7 papers on verification in SOSP and OSDI over the last 10 years. So like operating systems, like SEL4, distributed systems, file systems. So substantial verification projects. And if you look at what tools they use, well, there are these 3 projects over here that use Boogie and Daphne and Z3, or some combination of those, where the emphasis is largely on automation and SMT solvers. There are these other projects that use Isabelle Hall and Coq, where the emphasis is largely on expressive logics, higher order logics, dependent types, and interactive proofs using tactics. So it seems like there's still kind of these 2 classes in practice. But recently, there have been a lot of efforts made to kind of connect these two different classes here. So there are plugins where you can call out to SMT solvers from interactive proof assistance, things like Sledgehammer for Isabelle Hall and plugins for Coq as well. There are tools that support multiple provers, so maybe you can use, say, Z3 for some things and Coq for other things. And then, maybe kind of most intriguingly, there are some new platforms that seem to have a foot on each side in their very nature. So, and I'm sure there are a lot of systems that fall into this category, but I'll just point out 2, FStar and Lean, because those are things I'm familiar with. And so it seems like maybe there are some systems now that are really starting to walk this middle ground, and it's a good time to see what we can do given features from both sides here. So let me just focus on F star here. And so F star definitely has supported SMT automation, kind of in its very core type checker. So if you declare, say, a refinement type for natural numbers in the range 0 to 10, and a type for natural numbers in the range 0 to 20, you can then ask the type checker to type check a program that involves those types. And so F star is kind of based on ML, so particularly OCaml and F sharp. So it has a very ML-like type system. But this type system doesn't necessarily know anything about integers. If I want to call F, which takes a number up to 20, with a number that goes up to 10, F star has to outsource this to the SMT solver and ask the SMT solver to prove that x less than 10 implies x less than 20. And it'll just do this as part of its ordinary type checking. You don't have to invoke any tactics or anything special here. So when you start using F star, you get SMT queries right away. However, F star also supports higher order logic. It's very similar, in fact, to Cox's calculus of inductive constructions. As of this year, it now supports tactics as well. It supports full dependent types. And I'd like to say a little bit about that aspect in particular. So here's an example of using dependent types in F star. So I can have F take a Boolean and return the value. If B is true, then return 5, otherwise return true. I can actually give that a dependent type in F star. I can give it the type if B, then int else bool, and that is type checkable. And then if I invoke F with true, I'm able to show that the actual result of that has type int. And this is a standard feature of dependent type systems, and it relies on the type system being able to evaluate or interpret these types. So the type system, has to plug this value true in for B here, and then evaluate this expression if true, then int else bool to int, in order to type check that this can be assigned to x of type int. And it does this without any help from the SMT solver. It just has a little interpreter built into its type checker. And like I said, this is completely standard for dependent type systems. All right, so given these kind of features, what can we do? So we've been experimenting a little bit with some of these features, and a couple of our interns this summer are working on this. And let me in particular highlight just this block of code here. One of the things that Vale should do, in fact, its kind of purpose for existing, is to verify blocks of assembly language code here, and hopefully verify those as fast as possible. When we actually started verifying things, we were a little bit disappointed in the performance of this. So we had developed earlier tools. We had a tool called Boogie x86, which wasn't as flexible as Vale. It was tied to x86, for example. But the verification of blocks of code was actually faster in Boogie x86 than it was in Vale. And I want to show you why that's the case here. So I said that the Vale tool will generate lemmas when you pass it code like this. And these lemmas basically just call out to other lemmas. So this is the lemma for Poly1305 reduce, and it's just calling lemmas for and, move, shift right, and so on. And at first glance, this looks pretty efficient here. It's not obvious why it would be slow to verify this. But each one of these lines actually has a lot going on from the SMT solver's perspective. So we're manipulating state values, and these states have various components to represent the state of the assembly language system. So memory, status flags, register, a bit that says whether the execution is okay or is crashed. And so there's a lot of unpacking and packing of these components of the state that the SMT solver has to do, looking up registers in the register file and so on. So if we look at a particular example, the lemma for and has to do with just a bunch of little silly things, like check that the operands the destination source operands are valid. So they could be constants, they could be register operands, they could be memory operands. If they're constants, they have to be in range and so on. And it has to reason about framing. So which things in the final state SM have changed relative to the state S0 and so on. And maybe worst of all, it has to reason about evaluating operands in different states. So it has to evaluate the source operand, for example, by looking it up in this register file, which may involve reasoning about the update that the previous instruction did and the update that the instruction before that did. So there's a lot that the SMT solver has to unpack here just to check a single instruction. So the verification condition that we get out of F star is not quite as efficient as one that we would have written by hand. And so the performance tends to be a little slower. So, well, what if we just wrote our own verification condition? We can do that. F star is a functional language that you can write functions that generate terms that have existentials and ands and ors and so on in them. So let's just write our own strongest postcondition generator. So this is something that takes a list of instructions, an initial state, which let's assume is a precondition that that's in an OK state, and says that, well, if you execute a move instruction, that involves checking that the source is valid, evaluating the source, and then recursively generating a strongest postcondition for the rest of the instructions after having updated the state so that the destination register now contains this value x that we just computed. And likewise with and, here we have to update the status flags as well and do this computation of anding the destination and source together. So fine, we can write any code we want. We could write a strongest postcondition that just says true or false or something. What does this have to do with what we're actually trying to prove? So if we write a function like this, how do we connect this with what we're trying to prove about our actual assembly language instructions in the F star proof? And who's even going to call this strongest postcondition generator? So F star is busy doing its type checking. Do we want it to just stop and make a call out to our little plugin here? How's that going to work? So we kind of expected this to be hard to do. It was surprisingly easy. So to answer the first question of how we connect this custom verification condition to the F star proof, well, we just had to write a soundness lemma that says, given a list of instructions and some initial and final state, if the initial state is OK, and when we evaluate these instructions applied to the initial state, we get some final state, then we can ensure whatever the strongest postcondition says is true. And this was very easy to prove. It just took maybe 5 or 6 lines per instruction. Something that was very easy to prove in F star. And as for the second question, well, remember that this dependent type system forces the type checker to have an interpreter in it as part of ordinary type checking. We can actually just call that interpreter. And the magic word to call into the interpreter is normalize. So if we say that this function ensures normalize of some expression, then when we call this function, F star will substitute in particular instructions and states here, and then interpret this expression here as far as it can. So it'll go through and expand out this recursive function, apply it to these various patterns here for each instruction, and just generate a very large strongest postcondition, which is exactly what we want. So once we've got this lemma here, it's very easy to use. We can actually just take our old lemma that Vale generated, get rid of these 8 calls to the instruction lemmas, and replace them with just 3 lines. So some boilerplate to set up the verification of a block, a line that just creates a list of the 8 instructions that we want to verify, and then a call to our strongest postcondition lemma. And we just plug those in, rename a few variables, and it verifies. So that's actually was surprisingly easy to use. And the verification condition that ends up getting sent to Z3 is much more efficient than our original version of the code. So let me show you how that works. And I'll just take this list of instructions here as an example here. And let me rewrite that, expand those out here. These are our 8 instructions. And I'll show you just 3 of these, this move, this and this add here. And what happens when we try to run the F-star interpreter on those instructions. So let's take the move first. So we have to check that the source R10 here is valid. That's very easy to do. We just interpret the valid operand function, and it returns true. So that's done. Then we produce this term exists in X, such that X equals whatever you get by evaluating the source, which is R10, in the state S0. And we know that the source is a register. It's not a constant. It's not a memory operand. So the evaluator will immediately specialize that to look up R10 in the register file. Don't worry about these other cases, constants, memory, and so on. Now, if we move on to the AND instruction, we're going to evaluate this constant operand 3. That just produces the value 3. We're going to evaluate this operand RBP. But this time when we evaluate it, we're going to evaluate it relative to a register file that we've stored X into. So this move instruction puts something into this destination RBP using this update here. And when we go to look up what's in the map at register RBP, we will get this value X out of the map. So we evaluate map updates and lookups just like a normal programming language would. And so we get something that doesn't involve the state or components of the state or register file or anything like that. We just get X. Likewise, when we do the add instruction is going to refer to the X prime generated by the AND instruction. And so you see what you get here is something where everything is in terms of these variables introduced by the existential quantifiers here, without a bunch of additional overhead for reasoning about register files, states, and so on. And so this is the actual formula that F-star generates and then translates into something that the SMT solver can understand. And we're only just kind of starting to work on this. We've only tried this on small examples, but it's run anywhere from 1 to 5 times faster than our original naive lemmas did. And I should say that I'm not claiming that this is anything new here. This is very familiar in the interactive proof assistant community. It goes by the name reflection. So for them, it's very familiar to prove, say, some sort of soundness lemma about an algorithm and then run the algorithm using the type checkers interpreter to get a more efficient proof. So this is old hat to them. All I'm saying is now coming from the automated side of the world, we're simply wearing somebody else's hat. And so I'll conclude with that. So this is a little bit speculative, but the hope here, we're not asking for anybody to necessarily throw away their automation and use interactive proofs, but the hope is that maybe by starting to incorporate some of these expressive logic features into our automated proofs, we can actually use that to get better automation. So that's all I have to say. If you're interested in this project, all of our code is available on GitHub. You can find it here, and I'll be happy to take any questions.
So we have time for questions. If you have a question, just come up to the nearest mic. There's some here and
there. Just briefly, there's all the fun stuff that you're sort of talking about, intellectually interesting, but it seems like there's monumental effort invested into like those machine models and, I mean, like an x86, formally specifying what all the instructions. Do you have any comments about, sort of how painful that was? Do you share, is this also available for everyone to use? Could you make the world better in some way, to handle a new instruction set? Just any insight on just that part of the project?
Yeah, so one advantage that we do have is that we're definitely not trying to formalize entire architectures. The Intel manuals are thousands of pages long. We're probably trying to formalize 20 or 30 pages of that. These crypto algorithms, they do loads and stores. They do bitwise operations and adds and stuff. So we still have to do some work on the vector instructions. I would say that's probably the hardest thing. Probably the bad side of that is that we won't have a complete model for everybody else to use. But certainly, if people are interested in our subsets, they're out there on GitHub, and the operational semantics are in a pretty straightforward form.
Okay, quick one. So what's the biggest sort of pain point that you think would be tackled outside of sort of the core Everest team?
Outside of the core of what?
The core Everest team. So how the rest of the world could contribute? Well, first of all, there's a lot of work just on the Everest project. So anybody who'd like to, work on this project, we welcome them with open arms. And I think we've been finding that, as we've been focusing on TLS and crypto and stuff, we maybe haven't had as much time as we want for things like certificate handling and HTTPS and that kind of thing. So there's definitely a lot to work on and be valuable. And of course, better tools, we always welcome those.
Hi. The go-to-fail bug depressed the hell out of me. So this is written in C. This is probably not much of a choice. But then people decided you don't need to actually write a test case to see if your program fails when you give it a wrong certificate. After all, this is like the most security critical code we have, right? They decided you don't need to do a manual code review. Then they decided also you don't need to do a coverage analysis to see if you've actually tested the code that rejects any certificates. And we're spending millions and millions and millions on these wonderful formal methods, right? So my question in the end is, aren't we all on the wrong path entirely?
From the formal methods community, or are we not tackling the right problems?
Shouldn't we just be doing, this is stuff you learn in the first semester of computer science, right? How you test your code. Yeah. And people aren't even doing this, and we're doing whatever, theorem provers and
yes, I think I would consider them both valuable in the sense that, with really rigorous testing, you should catch the first 95% of the bugs. It's hard to catch the last 5, 3, 1% of the bugs. There are some projects that are making a really good effort in this. So I particularly like a project named Witchproof, which is named after the smallest registered mountain in the world. I think it may have been exactly the reaction you're describing to our work, that is really trying to test things thoroughly. And I think that is important, in the short term. We're certainly, even if we finish this project with crypto and TLS, there's a whole stack of stuff built on top of it that we're not going to get to. So we can hope to kind of tackle particularly security critical pieces of code. And beyond that, testing is essential, and code coverage and all of that.
If there are no further questions, maybe just one, maybe related to another aspect of what Roderick was asking about social angle to this whole thing, right? So do you think there will be a time when companies will be selling the pieces of software by saying, don't use this open source version because what we have done is invested a much more validation effort, or do use this open source version because it has been validated in this way, right? Either formally or using testing or something like that, right? Do you think this awareness is sort of coming of the importance of these techniques?
So in the security community, I think actually they are aware of this, and so a lot of the bugs that I showed, like Freak and Logjam and so on, Those actually came out of formal studies of the behavior of TLS using formal tools. So the people who developed like OpenSSL and other TLS implementations and crypto things are taking formal methods seriously. Now, in order to convince them that you should actually go to all the effort to formally verify every last line of code, that's a big step, and we have to demonstrate that that's possible before we expect them to be willing to take on something like that.
Thank you. If there are no further questions, let's thank the speaker again and have a break.